Welcome to CS 571. So we're still in the middle of the very last topic, I/O and storage. And this is the very first video of the Lecture 9B series, hard disk drive, okay? So first of all, what interfaces does a hard disk drive expose to the end users, basically to the operating systems, right? So Um, hard disk drive is a piece of mechanical hardware. So you can call it a magnetic disk because a hard disk drive uses magnetic film, this kind of material for memorizing the state, for storing the data, right? And this piece of hardware, internal, it it keeps track of an array of sector, which is called a sector addressable address space. Okay, so you can kind of think of a hard disk drive as a linear array, one-dimensional, 1D array of sectors, and each sector is also called a logical block, and each sector is the fundamental, the smallest unit of a data transfer, read and write, IOs. Okay, and this is the important thing that you need to memorize. You need to remember. The sector is a basic read and write unit in the context of a hard disk drive, because a hard disk drive is also called a block storage, and the same for a flash-based SSD devices. These kind of external secondary storage devices, they are called block devices. If you want to read one single 4-byte integer, say, you need to read this whole sector, you need to read this whole disk block out from the device, and the size of which is typically half a kilobyte or 4 KB, right? Half a kilobyte is 512 bytes or 4096 bytes, okay? So, and of course, since it's an IO device, it supports read and write operations. You can read out from the disk multiple sectors, multiple disk blocks, and you can write to the disk multiple disk blocks, okay? So this is a basic interface of hard disk drive. And typically, people call it disk, and this disk you can refer to as a hard disk drive. Okay, internally, how does a typical hard disk drive looks like? Well, as I've already mentioned, a hard disk drive is a one-dimensional array of logical disk blocks. And these multiple, like sequentially arranged disk blocks or logical blocks are mapped into the sectors of the disk, in a sequential manner. And sector 0 is the very first logical block of the first track of the outermost cylinder. So you don't have to understand all these terminologies, because in the next couple of slides we're going to go through all these like terminologies one by one: cylinder, platter, track, and so on. Okay. So in the next couple of slides, I like to use this a graph to kind of better illustrate how exactly a hard disk drive looks like internally. Okay, so here this circle is essentially a hard disk drive platter. It's just a two-dimensional graph. These couple of slides, it won't capture the 3D feature, because hard disk drive is essentially like 3D internally, but here it just captures a single platter, which is 2D. Okay, so this surface is just a platter, and on top of it, on the surface of this platter, is covered with this so-called magnetic film material, which is used for recording the state, recording the data. Okay, and you can read the data from the magnetic film, and you can write data into this magnetic film. Okay, and in this slide, it adds in more information. So here, it shows a single track, and this is the outermost track. Okay, obviously, a single disk platter can have multiple tracks. So this is the outermost track. So since this is a simplified example, it has only 12 sectors. As you can see, sector 0 is the very first sector starting, is shown on the right-hand side, and the last sector of the outermost track is shown above it, which is sector number 11. Okay, obviously it has multiple sectors. Okay, and in the center of this surface, this platter, is what is called a spindle. Okay, and we could have multiple platters, and the center of it uses single spindle in the center across all the platters. Okay, which will be shown in the one of the future slides. And basically the surface, the platter is spinning around the spindle as a center point. Okay, and the track is further divided into multiple sectors, which each and every one of which is the basic read and write unit of a hard disk drive. Okay, so here it shows more information, more pieces of hardware parts. So it shows what is called a disk arm. Okay, over here, and at the end of this disk arm is what is called a disk head. And essentially, this piece of hardware, this part, which is called disk head, is the piece of unit which is responsible for data reading and data writing. Basically, you need to read the data from the platter, one of the sectors located on a single track on top of the platter by using the hard disk head. And if you want to write data to the magnetic film, the data should go through the head as well. And in this particular toy-like example, this platter is spinning like counterclockwise. It rotates this way, okay? Counterclockwise. All right, so in this slide, it shows a more comprehensive three-dimensional view, okay? It shows how it looks like. It more resembles of how a real-world hard disk drive looks like, okay, internally. In this case, we have multiple platters that are stacked with each other, and in the center of all of them is a single spindle in the center, okay? And on this dimension, on this cylinder, is a single track, okay, which is called track T. And within track T, this random sector is called sector S. And we have the cylinder over here, okay? And on the right-hand side of the slide, it has a single disk arm assembly. And this arm assembly has multiple disk arms. And at the end of each and every disk arm is the disk head. And as I've already mentioned, disk head is the one piece of unit which is responsible for reading data and writing data, okay? And which is not like the previous example, simplified example. In this case, all these platters, they are rotating, they are spinning like clockwise. So they're rotating clockwise direction, okay? But in a typical question, you'll be given the assumption that is provided where we specified the rotation direction of a disk platter, okay? So in the next couple of slides, I'm going to show you, using this simple example, how a hard disk drive read a sector, read a data, read a logical block of data from a particular track. So in this example, let's read sector 0. And it's a more comprehensive example. So in the center, it has a spindle, and on the surface, it has a total number of 3 tracks. And let's first take a look. Let's first try to locate where sector 0 is. Right now, sector 0 is over here, right? And assuming the disk platter surface is rotating counterclockwise. So in order to locate to sector 0, the whole piece of hardware is needing to go through the following 3 steps. So step number 1, the disk arm needs to seek for the right track, and right here, sector 0 is located at the outermost disk track. So your disk arm needs to seek like towards the outer direction. Okay, so this is the first step. And the second step, the surface is, the platter is keep rotating. Okay, but in real world cases, step number 1 and step number 2, they are essentially happening like kind of concurrently, simultaneous at the same time. Okay, so I need to rotate till when the disk head has a clear focus on the sector of request, which is sector 0. Okay, so in this case, you need to keep rotating from sector 0 all the way to sector 0, from sector 9 all the way to sector 0. And then followed by the last step, which is step number 3. When you have a clear focus and when the head is targeted at sector 0, you could just read the data out, which is the last step, transfer the data, okay, which is a read operation. And remember, it always read the whole disk sector out from that logical block, okay? All right, so in this slide, it shows this URL points you to a YouTube video. It's a phone watch. So basically, what it shows is it shows the someone opens up its hard disk drive and it powers up the disk, and he performs some random operation like random read, random write, sequential read, sequential write, and the fragmentation kind of different operations. And it will show you how exactly like different pieces of mechanical hardware work together to facilitate like different operations. It's an interesting watch, but it's a little bit dangerous, so please don't try that at home yourself, okay? Don't do that. All right, so here, it talks about how we could possibly model a disk performance. So how to quantify disk performance theoretically. Okay, recall that a hard disk drive is a mechanical piece of hardware, right? It consists of multiple mechanical parts. It consists of like disk arm, disk head, and the platter, and it has, on top of the platter, has multiple tracks. So that means a typical, in order to finish a typical I operation, no matter whether it's a read operation or a write operation, it needs to involve like the movements of all these different pieces of hardware, right? So we could refer to this simple equation to kind of model the disk performance. And this equation consists of 3 parts. The first factor is the seek latency. This is the time it takes for the disk arm to seek for the right track and settle on the right track. So this is the seek latency, okay? And the second factor is the rotation latency. And that is the second step, remember? And you need to, the hard disk drive needs to, power up the rotation process. So the platter is keep spinning until the disk head is under clear focus of the requested disk sector. In the previous example, remember, it rotates from sector 9 until sector 0 because sector 0 is requested data. So this is the second factor. And the third factor is the disk data transfer, okay? So it combines all these 3 steps together, and it aggregates together to give you a theoretical performance number, okay? And typically, the disk access latency is at millisecond level. And 1 second is equal to 1,000 millisecond, okay? Which is extremely slow if you're talking about like I/O or read and write performance. And remember, the memory latency is at a nanosecond level. Okay. So let's see. How should we model each of these three different parts? Let's first take a look at the seek latency. Okay. So first of all, seek, it may take several milliseconds to settle down, right? Only the settling itself. So that means when it starts to move and when it tries to stop the moving. So this is the settling process. It has like two different parts, right? Before it starts to move and before it stops the moving. Okay, so this part in total takes around like half a millisecond to 2 milliseconds, which is kind of long. Okay, and entire seek often takes, including the settling process, it typically takes like 4 to 10 milliseconds. So this is an empirical results. So we don't need to like calculate it on our own. So it's always given, like it's empirically measured 4 to 10 milliseconds. Okay, so this is a very first factor, seek latency. And moving on to the second part, rotation latency. So often we use such a performance metric, which is called RPM, which is the short of rotations per minute to kind of quantify the performance of a typical hard disk drive. So nowadays, a common RPM value is 7,200, sorry. And the sum of the high-end hard disk drives, it could have like 15,000 RPMs. Okay, so these are typically more expensive high-end hard disk drives, which is faster, like 2 times faster compared to 7,200 RPM disk. Okay, and some older computer, it might be equipped with like old-fashioned hard disk drive, which typically had 5,400 RPMs, which is really slow, to be honest. Okay, so how to calculate the per rotation latency is we could use this RPM metric. So how to calculate is just 1 minute divided by, because this 7,200 is the total number of rotations per minute. Okay, 1 minute divided by 7,200, and you translate this into the unit of second, and also the same times you convert it into per second rotations. Per second rotations is 120, given an RPM of 7,200. And this further gives us, 8.3 milliseconds per rotation. Okay, so this is still not the end of the calculation. In order to quantify a rotating latency that makes sense statistically, we need to further do the following operation. So we need to cut it half, basically, to divide this 8.3 millisecond by 2, which gives you roughly 4.15 millisecond or 4.2 millisecond. So this is kind of statistical result. This is something on average results, because intuitively, let's say, so how to understand this is, let's say we're talking about the surface, and let's focus on the outermost track, right? And this is the disk, a disk arm and disk head. Okay, so randomly, if your sector of request happens to be over here, you don't have to rotate like halfway. Instead, you just rotate 1/4 of the total, like the full circle distance. If your disk arm, this head happens to be over here, and this is your data of request. But on the other hand, let's say and assuming it's rotating this direction, like counterclockwise, okay? But let's assume your data is over here, right? Then you have to rotate all the way, okay? Which is like, let's say, 3/4 of the full distance of full, right? So statistically speaking, almost half of the chance, your data is located this half, and another half of the chance, your disk located on the other far half. Okay, so that is how we basically need to just cut it into half, and we just get the 1 second of it, okay, which is roughly 4.2 milliseconds. So this is the whole calculation process of how exactly we quantify rotation latency. All right, moving on to the third factor, which is a disk transfer. And we could say that it's relatively faster and depends on, RPM and the sector density. Typically, we're looking at 100 plus megabytes per second, and we also call it disk throughput, okay? And this is typical result for typical performance number for SATA 1 disk. And for some high-end hard disk drive, it could reach to up to like 600 megabytes. This is extremely fast, even faster compared to like some of the flash SSD devices, okay? So how to calculate the transfer latency is, so over here, under the third bullet, it gives you an example. Let's assume the sector size or the disk block size is 0.5 kilobyte, 512 bytes, okay? In order to quantify the latency it would spend to just transfer out a sector worth of data, which is like 512 bytes of data, it takes this long, which is 4.9, almost 5 microseconds, okay? And here we're looking at microsecond, which is not at the same order of magnitude that we were looking at, in terms of performance metric. Like before, secant rotating, we're talking about like millisecond level latency. And here, if you were talking about to read to read the 1 sector of worth of data out from disk, it only takes like microseconds, okay? So assuming the disk bandwidth is 100 megabytes, 1 second divided by 100 megabytes translated into 10 milliseconds divided by a single byte, and further translated into like 4.9, which is almost 5 microsecond per sector. Okay, so this is the third factor. All right, so let's put this equation, let's put this performance model into some context. So the fundamental question to ask over here is, what kind of workload is best suited for a hard disk drive, for a mechanical hard disk drive? Right here, we're talking about magnetic hard disk drives. So because we've already seen the seek operation and rotation operations, they are relatively slow as compared to the transfer latency, as compared to the transfer speed, right? Even if we're talking about like relatively low end hard disk drive, which is equipped with 100 megabytes per second disk bandwidth, still data transfer is relatively faster. But what kind of workload is best suited for disk? Obviously, the workload that could take advantage of this sequential disk bandwidth, namely large sequential reads, large sequential writes. So the answer is sequential I/O, right? Sequential large I/O, because you could just access contiguous consecutive sectors in order, right? In order to transfer the data out from disk or transfer data into the disk. And this is, transfer dominated, and assuming transfer is the fastest factor among all these 3 different factors that determine the disk latency, the disk performance. Okay. On the other hand, what kind of workloads are especially bad for hard disk drive? random workloads, random small IOs, okay? So that means on the random IOs, your disk arm, your disk head, and as well as this platter, the surface, needs to be like working like crazy, right? It needs to like spinning all the time, back and forth, and the sector and the disk arm and the disk head needs to like moving back and forth, seek back and forth, because it is dominated by these random IOs, and all the small IOs are randomly spread across a huge range in terms of cylinders and tracks. Okay, so this is typically slow on disks. So the caveat over here is the crux is never do random IOs unless you must. For example, quick sort. Out of core quick sort, meaning your data is large enough, it's too large to be fit into the main memory. So you have to constantly read data out from the disk for this kind of out of core quick sort like operation. It's just terrible for hard disk drive. It's just extremely slow, okay? Because it's not able to take advantage of this relatively super fast sequential throughput. So let's further put this into a specific example context. Here we're looking at Seagate Enterprise SATA 3 hard disk drive. And in this table, it lists a bunch of 3 performance metrics, namely RPM, rotations per minute, which is 7,200, and average seek latency is provided, which is 4.16 milliseconds. And the max transfer bandwidth is 500 megabytes per second. So the question here is, how long does an average 4 KB read takes? Let's assume this hard disk drive is configured to use 4 KB as its basic sector size, or the basic disk block size. Okay. Let's first quantify the transfer speed. So transfer 1 second per second, 500 megabytes. So 1 second divided by 500 megabytes times the total amount of data that you want to transfer, which is 4 KB, which gives you 4 microseconds. Okay, this is extremely small. And then let's take a look at the whole latency. Recall that the whole latency is determined on 3 factors. The first one is the average seek latency, and the second one is average rotation latency. Average seek latency is already provided, which is 4.16 milliseconds. So how to quantify average rotation is, recall that we need to look at this first metric, which is RPM. For 1 minute duration, it rotates like 7,200 times. Okay, so it takes around 8.3 milliseconds, just as we've already calculated in one of the previous slides, to finish this full circle rotation. Okay, per rotation takes this much, and statistically speaking, we cut it half to give you this 4.2, approximately 4.2 milliseconds. Obviously, the first 2 factors, they are the dominating factors, and the performance is dictated by these first two factors. If we're talking about like small rates. Small reads meaning, like just read 1 or a few disk sectors, okay? And the unit is dominated obviously by milliseconds. And this part is just too small to be ignored, to be omitted, okay?